Our last topic of section 15.4 is double integrals can be used to find areas. So far, what we've been doing is we've been finding volumes with a domain that is two-dimensional. And so now we've gone over our rectangular domain in various ways to treat that. And then we've gone over now how to handle a polar area in the r theta plane. So double integrals, it turns out, can also be used to find areas. So something I skipped from 15.3 and just am coming to it now when we need it is equation 10. So what this says here in this red box is that we have a double integral over the domain of 1, which would correspond to the plane z equals 1. So if we do that integral, it seems kind of trivial, but what you would get if you did it would be the area of the domain. So let's kind of talk about why that would be the case. I think it's helpful to maybe go down to the cylinder here and think about the volume of a cylinder. So that would be v equals pi r squared h. So this would be specifically in our scenario here where a domain was circular in the xy plane. But if you let your height equal 1, then the volume would be pi r squared, which is exactly the equation for the base area. It's just the equation of the area for the circle. So because we have, when we have z equals 1, we could think of this as having this unit height, that would be the volume as depicted here with this figure from your book, or with this cylinder here. That volume is pi r squared, but noticing that it's always equal also to the basal area, we can use that to find the area of the base. Okay, so we could do these integrals with one integral, but it turns out it's simplified in a lot of ways with the double integral. And so to illustrate that now, we go to this next example here. So in Calculus 2, we did do polar area, and we're going to rework a problem from Calc 2 with this idea that we just learned, that we can use a double integral to find an area if we integrate over the domain and we just integrate 1. So here it says use a double integral to represent an area inside one petal of the rose shown. These don't really look like roses, but that's what they're called. The curve is defined by r equals 3 cosine of 3 theta. You need to set up the bounds and inside of the integral in terms of polar coordinates. Rectangular would be impossible. So this idea here that we can calculate area, all your other problems are volumes, so these kind of stick out in that way, with the double integral over the domain, but we're specifically going to integrate 1, the z equals 1 surface, and that's how we get to it. And that will be equal to the area. So here for our r goes from 0 for one of these petals. Picking this one that's right here on the pole would be best. And then it's going to go it's going to go to 3 cosine of 3 theta, or the given equation. So we're going to have variable bound in 0 for our r. That's going to go in the innermost set. So we did this in a prior example where finding theta, you can use the fact that it's going to come back onto itself, its graph, when r equals 0. So if you solve for 0, there's a lot of solutions, but if you're looking in the neighborhood of this petal, a solution around 0, a theta equals 0 in that neighborhood, you can just get rid of the 3 here. The way I like to do these is treat 3 theta like some other angle, gamma, I guess, and then cosine of gamma would be, what would that be? Well, gamma would be pi over 2 and negative pi over 2 in this neighborhood. Gamma was actually 3 theta, so now to solve for theta that we want, because that's actually what we want, then divide by 3 here. So our theta is equal to plus or minus pi over 6. And so those are our bounds for our theta when we plug it into the integral. So doing that, we are just integrating 1 when we do this, we're trying to find the area, not a volume. And so we just need to put in all these parts. So we have our bounds for r, we have our bounds for theta, and then don't forget that for dA, you always plug in r dr d theta, or it could be d theta dr depending on how you're setting this up. For us, we have to put dr first because we have a variable bound for r. So we do that, and then you end up getting 1 times r, which is r, easy integral. You do it, and you get 1/2 r squared. So kind of a cool thing happened here. I say here that you're not required to go beyond this point. Like, I'd probably just have you set it up but not solve or something, because sometimes this integral ends up being kind of tough and requires a trig identity and trig integration. But I want to show you something really cool. So anyway, if you just stick with me for a second longer, well, more than a second, but a little bit longer, notice when you get this 1/2 r squared thing, that probably don't remember, but I'll remind you here that that is pretty much the equation for the area of a polar region that you learned in Calc 2. Whether you remember it or not, here it is. A to b is the integral 1/2 r squared d theta. And we could derive that using other principles, but notice that that's what we got when we integrated 1 with respect to the polar r dr thing. And that's where it comes from. This is a different way to derive it. So anyway, I just kind of went through and decided to call attention to that here when I worked out the notes with the limits of integration plugged in. We had the 0 in there, so that's why that worked out nice. And then this is what you'd have to do if you needed to finish it with a trig incorporating a trig identity. So that's it for the notes. You have an example that you have a homework problem that has to do with this. And a lot of times it might be just setting up if it's ends up to be a hard integral, aka a trig integral, one that requires an identity that's not the Pythagorean identity, which is sine squared plus cosine squared equals 1.